Okay, so finally we can start discussing some of the current advances in technology which are starting to allow us to conquer some of these hurdles which you just talked about. First, let's look at the strides which have been recently made to improve hardware. Right here. So if you remember, we spoke about hardware in two different instances in the presentation so far. When we were talking about first we talked about the physical barriers, the quantum wall, and thermal power wall, which processors are starting to hit. This right here, it's for the GPU and the CPU as well. A bit later in the presentation, we then talked about the data bottlenecking problem, which occurs between processors, between the GPU and CPU. So the future looks pretty bright for being able to overcome these two hurdles. In February 2012, physicists created a working transistor. Transistor is a thing that holds the bits to make the memory and information storage possible. And so in 2012, physicists actually created a working transistor consisting of a single atom. Although there were other attempts at single atom transistors, this transistor had a greater probability of achieving the desired results compared to the previous attempts. This was a great breakthrough because for the longest people thought that this might be impossible due to some of the laws of quantum mechanics, such as the Heisenberg theory, which has recently, maybe a while back, been updated and tweaked a bit. So after single atom transistors, or perhaps at the same time as the single atom transistors are being developed and produced commercially, photon transistors will come onto the scene. Several companies are hoping to replace these traces on the circuit boards with optical signals. There has been a lot of funding going on in processor hardware research. In 2010, both Intel and IBM joined forces, investing $4.4 billion into chip technology. So in conclusion, due to these hardware advances, we should not have to worry about hitting the thermal power or quantum wall anytime soon. Moore's Law will continue without a problem for at least the next several decades. Okay, so now let's go on to talking about bottlenecking. Remember the limitations with the heterogeneous or hybrid computing model was the significant overhead incurred due to the data transfer between the host CPU and the GPU. Well, both IBM and Intel, once again, are both independently investing money and time into photon data transfer technologies. They're both working towards replacing copper cables and backplanes. The backplanes are the things which connect the CPUs, GPUs to the rest of the circuit board with photon data cables. Also, photon data transfer significantly reduces the CPU to GPU communication and brings data transfer rates down, hopefully to negligible times. So that would be really a positive thing for hybrid computing. Okay, so next we're going to look at some pictures of these new advancements we've just talked about. So up on the top left, you'll see the single atom transistor. In the center here is atom. Here's the little gully that it flows along. Then inside this L-shaped region, we talk about the photon transistors and the photon cabling within the computer. In the IBM article, which discusses their current research, it went over their timeline plan. In 2008, they had hoped to replace electrical cabling with optics, and you started to see that back a couple years ago when companies such as AT&T, UVerse, and Verizon started offering data transfer via fiber optics cables. Then in 2012, this year, they had hoped to replace electrical backplanes with optical backplanes. And you have seen maybe one company, I think it was, I had it listed in my report, but I think we saw one company that started to produce optical backplanes electrically, optically, but you really haven't seen that many optical backplanes in the market yet. But they are starting to come out in 2012. In 2016, they had hoped to replace the electrical printed circuit boards with optical printed circuit boards. So here you see a circuit board. This is what they'd hoped to do, is replace all of the copper cabling, which you see when you look at a printed circuit PCB, with optics. So these would be optical data transfer lines in the printed circuit boards. Then in 2020, they had hoped to replace or conduct data transfer via optics on the chips themselves. So here we see one of the optical chips which IBM was proposing. This is called OptoChip, and they were hoping to get this produced by 2020. So this is their plan so far. This is how different companies and programs are hoping to solve the hurdle of hardware when it comes to GPU, CPU. Okay, so next we come to the hurdles in parallel programming. Currently, programs written for an architecture with N processors require a rewrite when migrated to an M processor architecture in order to benefit from additional resources. And this makes programming for GPUs cumbersome. Although the compiler-based parallelization techniques try to automatically find and use partial order sequential code, they often fail to match the manual optimization. One article describes several shortcomings to the architectures listed below. First off, POSIX requires programmers to specify the partial orders between program operations in terms of constructs such as threads, locks, and semaphores. OpenMP requires programmers to specify code which they believe would perform better via parallel processing. When it comes to OpenCL and CUDA, these require user knowledge of the computational platforms, and you would also need to learn the libraries and how to implement them. So what are some of the solutions? Groups are hard at work attempting to make parallel programs easier